Welcome to the Geothermal Liftoff webinar. And for those of you who don't know me, I'm Vanessa Chan. I am DOE's Chief Commercialization Officer and Director of the Office of Technology Transitions. And our office has been the one that's been quarterbacking many of the liftoff reports that all of you all know fondly. For those of you who are not familiar with the Liftoff Initiative, just want to share you a little bit of the background. Here in the Biden-Harris administration, we set two goals for the country: a carbon emission-free energy sector by 2035 and a net zero economy by 2050. These are very audacious goals, but the Department of Energy believes that they are achievable. And hitting these targets on these timelines are going to require significant changes in industrial and manufacturing processes, transportation systems, and how we generate and transmit power. So the key to making these changes is understanding the state of every sector right now and what we need to do differently to hit the 2035 and 2050 timelines. And so to set this baseline, DOE launched the Pathways to Commercial Liftoff, and this huge data-driven effort starts with deep engagement with the private sector, because ultimately it's the private sector that is going to be commercializing technologies. We also involved all of DOE and experts from the national labs to determine a shared fact base. The goal is to get every single person, academia, industry, investors, inventors, labor, nonprofits, governments at all levels, on the exact same page so we can catalyze and accelerate the clean energy transition. The Liftoff report breaks down the value chain of various portions of the economy and sketches a roadmap for the private sector to actually deploy the solutions that we need. So in basic terms, what costs have we hit? What technological and market-driven barriers do we have to overcome? What's the amount of investment that we need, by when and where? So the liftoff term represents the point when solutions and their markets become largely self-sustaining, and we don't depend on significant levels of public capital, instead attracting private capital with a wide range of risks. So some people may have noticed an important distinction the liftoff assessments make: private versus public sector investment. And DOE's guiding principle is that the energy transition is private sector led and government enabled. And that's really, really important. And that's a big role for government to play. For instance, providing top-notch market-based research like these liftoff reports. And in the end, we hope these supporting roles that we're playing was really going to enable the private sector to work with us to get us there. So far, we have released 13 liftoff reports, and all of them are available at liftoff.energy.gov. That's liftoff.energy.gov. And our latest covers geothermal heating and cooling. Before we get into a detailed briefing on this report's findings and recommendations, I'd like to welcome two other senior members of the DOE team who also have been working on the liftoff effort with us for a virtual fireside chat. So first, I would like to introduce Jigar Shah, who is the Loan Program Office Director. And next is Lauren Boyd, who leads all the work in geothermal for the department. So let's start with you, Lauren. Can you give us a quick overview of why geothermal heating and cooling and geothermal heat pumps are in particular important?
Absolutely. Hi, everyone. And thank you so much, Vanessa. It's super exciting to see this report released because it articulates how geothermal heat pumps, or GHPs, as we'll say many times throughout this webinar, can provide a resilient and an energy efficient future. And it walks through exactly what needs to happen to get to that future. And this is one of the many reasons that I really appreciate the Liftoff initiative. As you described, these reports always provide a really actionable path forward. So GHPs, they essentially offer this cost-effective solution for heating and cooling. And the reason that matters is because a significant portion of US energy consumption, of global energy consumption, goes towards space heating and cooling. So what GHPs are really doing is essentially just leveraging the constant year-round temperature of the shallow Earth. And what we do is transfer that heat from basically to the ground and out of the ground by circulating water or other solutions through underground piping. It's essentially akin to a refrigeration cycle. So GTO, our office, has been focusing on GHPs for quite a while. In 2023, with the national labs, we published a study that confirmed that GHPs can provide significant benefits. So for homeowners, for renters, for building operators, because they span residential to the buildings and commercial communities. But also importantly, they can significantly reduce the need for more grid infrastructure, which is really important. And so even though they use electricity, they're so efficient that they actually in, net, basically, essentially overall, they use lower electricity, which means, of course, a reduction in our peak demand. So they can be utilized in new construction, they can be utilized in retrofits. And what's exciting about that is that it creates a really significant opportunity for consumers and for the grid as we replace lots of aging infrastructure. So just a couple of highlights of why GHPs are exciting and what they can do for the country and for US energy consumers.
That's awesome. And, it's something where this is one of the favorite technologies of the secretary for the many of the reasons that you talk about. And so, Jigger, I just wanted to pass it to you to really give us the bottom line up front of what this report is telling us.
Thanks. The report is quite extensive, and I encourage everyone to read it cover to cover. But distilling it down, I'd say utilities have agreed to bold decarbonization goals with their state regulators, such as the DTE gas loan that we recently announced. As a result of these goals, we will get geothermal heating and cooling liftoff when the equivalent of 7 million homes have installed geothermal heat pumps, which is a total cumulative market opportunity of $100 to $150 billion. Reaching that marker will require focusing first on scaling our capabilities in the near term through the year 2035, so over the next 10 years. And in this case, that means focusing on geothermal heat pump deployments in new builds. For utilities and developers expanding into new territories, that means building thermal energy networks, networked systems of geothermal heat pumps from the starting gate instead of a more expensive extension of these existing gas grids. After liftoff, the objective is to reach full-scale deployment. To hit that level, the industry needs to lean on some of the capabilities built to reach liftoff and start scaling up retrofits as well. To hit that level, the industry needs to lean on some of its capabilities built into reaching liftoff and start scaling up retrofits of infrastructure that have reached end of life. And by 2050, we could have the equivalent of 36 million homes with geothermal heat pumps and a total cumulative market opportunity of $500 to $700 billion.
Wow, those are big numbers. And I know, Jigger, you always like big numbers. And I think the question is actually, Lauren, can we do that? Can the technology actually get us there? Where it can be used and what makes it so beneficial?
Yes, so I think that the versatility of geothermal heat pumps is really critical here. So they can be utilized in all climates, and also another unique aspect of them is that they can be used in a variety of different configurations. And so we can essentially heat and cool individual homes or businesses. But as Jigger said, they can support networks also of buildings. So college campuses, hospital campuses, cities and neighborhoods. And in fact, we're seeing a massive growth in the number of college campuses around the United States that are opting to deploy large-scale geothermal heat pumps. So the beauty, I think, of these thermal energy networks, and it's outlined incredibly well in the report, especially the thermal energy networks that include GHPs, is that they can be customized to meet specific thermal energy loads. So just heating or heating and cooling. And regardless of that configuration, they're networked effects. So the opportunity to share simultaneous heating and cooling loads from all these different sources means that they're extremely efficient and that they could be used almost anywhere, to your question, Vanessa. So I think if you think about, utilizing waste heat from a data center or a sewage line, perhaps as your source of heat, that heat would otherwise be wasted. And then your sink can be residential or commercial buildings, for example. So we can use these in urban environments. We can use them in rural environments. The example that my office loves to use is St. Patrick's Cathedral in New York City. I'm from New York, and I think there's no better proof of their versatility than being able to drill and install a geothermal heat pump system in pretty much peak urban density in Midtown Manhattan. So we love that example.
Ooh, I had no idea. I've been to that cathedral. I'll have to go look for the heat
Yeah.
pump next time. So, right now we already use a lot of different systems. And so, Jigger, why should we use geothermal heating and cooling? Like, what's the value proposition compared to other forms that we can actually get heating and cooling?
Well, geothermal heating and cooling systems have a long track record of success, especially on very cold days and very warm days, where air source heat pumps have a little more struggle. The authors of the report will go into further details on all of these points, but I do want to highlight a few. First, geothermal heat pumps are the most efficient heat pump option in most states, which means the potential to reduce energy bills is the highest among all options for heating and cooling electrification. And because of that, there are really large potential grid savings and benefits when these systems get adopted at scale. One other aspect of geothermal heating and cooling that I'm excited about is that much of the investment in these systems flows to local and regional workers and small businesses because of the localized nature of geothermal heating and cooling value chains. I also want to emphasize that additional benefits that come from networked systems of geothermal heat pumps that we call thermal energy networks. Thermal energy networks have all the benefits of geothermal heat pumps, but they can be built with project level financing, my favorite, and are well suited for natural gas utilities, which means that they can serve many customers who might not be able to pursue a single building system. Gas utilities with decarbonization goals can consider thermal energy networks as a potential low carbon option for new infrastructure, providing heating and cooling as a service, often as a less expensive alternative to new or replacement gas pipelines. Some utilities are already pursuing pilot deployments like Eversource at their Framingham project in Massachusetts. And LPO loans from our 1706 Energy Infrastructure Reinvestment Program could provide much lower cost financing over much longer periods of time to make this option even more affordable for utility customers. Back to you, Vanessa.
Thanks, Jigger. So, Lauren, this is really bold. There's a lot of stuff we want to do, and I always like to be able to track where I'm going. So, what metrics does the industry need to hit to get to liftoff? And what are we doing here at DOE to actually help the industry achieve these really ambitious goals?
Yeah, so we're doing quite a bit. And I think that we have a lot of opportunity to make an impact in this space. So to get to that 36 million GHPs in 25 years, one of the things that we're focused on right now within GTO is tackling building a robust GHP workforce. So we have a prize that recently was released called our GHP Paths Prize that's going to be focusing specifically on that. And another initiative that's been underway for a few years called Community Geothermal. So I can talk about that as well. But I think something that's been a critical part of our portfolio in general is the opportunity to learn by doing in the field and use pilot projects to help reduce risks, to generate knowledge. And we're talking at much earlier stages than some of the work that happens in other parts of the department. But that opportunity to reduce risk, to generate this knowledge, to provide best practices to the community is really important. Of course, the non-dilutive capital and loan guarantees from public sources are really important too for this development. And we're seeing that have a very significant impact on deployment of thermal energy networks, at least on and within our program through this community's effort, where we've just released $38 million for 5 communities around the US to try to install TENS or thermal energy networks in a variety of different geographies around the US. The other pieces that I think are really important that we can have a role in are driving consumer interest in these systems. And this is going to be a partnership, of course, but so we have to raise awareness. That's something we're working on across the department and through this report, but also through cost savings and rate structure innovations and utility savings programs are detailed in the report. And I'm sure the authors who are going to speak next will talk about that. Finally, clarifying regulations. This is critically important. There's so many entities and jurisdictions that regulate this permitting process for drilling shallow boreholes, and then licensing and certification programs, standardizing those across the sort of different knowledge, skills, and abilities required to advance this workforce.
That's amazing, Jigger and Lauren. I really appreciate you guys giving this primer on geothermal heating and cooling. You've really warmed the room up, for our deep dive really, really well. So before the experts behind this report come on, I'd like to ask for some help from our viewers. Liftoff reports are both collaborative and living documents that we intend to update regularly. In fact, we just updated the hydrogen liftoff report. So we'd like your thoughts on the current report. What did we get right? What did did we miss, as well as your ideas for what we should investigate, include in the next iteration. And so we want to keep improving this material so that it has the maximum catalytic effect across the ecosystem. So please drop us a note at liftoff.energy.gov/input. And you also can find the Liftoff webinars as well as the other reports there as well. And so with that, I'm excited to introduce three doctors. Dr. Charles Gertler from DOE's Loan Programs Office, Dr. David Wong and Dr. Tim Steeves, both from DOE's Geothermal Technologies Office. And the three of them were the co-lead authors to this liftoff report. They're going to get into the nitty-gritty of geothermal heating and cooling, informed by interviews with industry stakeholders and DOE experts. And I'm certain that this presentation is going to spark further dialogue on how to scale and implement geothermal heating and cooling as part of resilient and sustainable energy future. So Dr. Charles, David, and Tim, take it away.
Thanks so much, Vanessa. And good afternoon, everybody. My name is Tim Steeves. I'm an ORISE Fellow in the Department of Energy's Geothermal Technology Office, as Vanessa just said, and one of these three related authors, along with Charles and David. Over the past year, really, we've had the privilege of working on this report with so many different collaborators across DOE and across the heating and cooling, geothermal heating and cooling industry. It's been amazing, and many of the people here I know have been invaluable in giving input on these reports. So we're really excited to share all our findings today. And those to those watching now and those who will be watching later on the website, as a reminder, you can download the full report and rewatch these webinars at liftoff.energy.gov. And before we dive in, really want to reemphasize Vanessa's point. These are living documents. Your input is still valuable and can still affect updates to the report moving forward on this subject and on many others. So please feel free to reach out and give your input at any point to us and on the Liftoff team. So with that, let me pass it over to David to discuss the report's top line messages.
Thank you, Tim. My name is David Wong. I'm Technology Manager at the Department of Energy's Geothermal Technologies Office, also known as GTO, one of the applied energy offices here at the DOE. And we are going to first go through some high-level findings here. And then we'll take you through some highlights and point out where even more detail can be found in the report that isn't available in this very short webinar. So first of all, geothermal heating and cooling technologies are an important part of the solution set for a resilient and reliable and efficient water and space conditioning technologies for homes and businesses. GHPs, or geothermal heat pumps, operate similarly to other heat pumps, such as air source heat pumps, in that they use a refrigeration cycle to move heat for heating and cooling. However, instead of outdoor air, as Lauren mentioned earlier, GHPs use the ground as a source and sink of heat because of the nearly constant temperature of the shallow subsurface year-round. Geothermal heating and cooling technologies can reduce peak electric demand. They can increase energy resilience, and they can overall lower ratepayer energy bills in a lot of cases. These systems have a unique value proposition amongst the building decarbonization technologies. It's a multi-pronged value proposition, which we'll unpack here in this webinar and is unpacked in more detail in the report. While GHP systems in many cases have a lifetime net positive value, the initial capital cost of standalone systems, standalone GHP systems, can be high relative to other heating and cooling solutions. However, we have found that in some cases, actually, geothermal heat pumps can be the lowest first cost option. We'll give an example of that later in the talk. We find in this report that geothermal heating and cooling can reach commercial liftoff by 2035 by first scaling up near-term opportunities in primarily new construction buildings. This represents roughly $100 to $150 billion in potential invested capital, or the equivalent of 7 million average-sized homes. So a fair amount. This could also end up reducing US winter peak demand by over 40 gigawatts. Later on in the report, we'll go into some imperatives that we think are pretty key to realizing that value proposition that's laid out there and that amount of investment. And with that, let me hand it over to Charles to discuss Chapter 1.
Excellent. Thank you, David.
Good afternoon, everybody. Charles Gertler. I'm a senior consultant in the Department of Energy's Loan Programs Office. I'm the third and final lead author of this report. So just going through some of the key takeaways first here from Chapter 1, and then we're going to jump into some of the selected analyses. But Chapter 1 is sort of the introduction to geothermal heating and cooling technologies. Describes how they can simultaneously help achieve energy security, energy efficiency, customer resilience, and energy affordability goals at scale, and help manage some emerging load and peak demand growth issues. And so David described how GHPs operate similarly to air source heat pumps. Chapter 1 also goes in detail into the benefits of connecting buildings via piped fluid at ambient temperatures, the thermal energy networks, or TENS, that leverage the benefits of GHPs. So I promise, I think the only two acronyms we'll keep using over and over again are TENS and GHPs, but they're important ones here. And we'll also describe the value proposition in detail. So Tim, if we can go to the next slide, I think we'll start just by describing what actually are geothermal heating and cooling solutions. So they use the ground and the source. They use the ground as a source or sink of heat, circulate fluids, often connected to heat pumps, to maintain temperatures in buildings. Importantly, they can serve as single buildings, they can underpin network systems, and our report focuses on geothermal heat pumps, GHPs, which are the systems that use heat pumps in the shallow earth from a few feet below the ground to about 300 feet. And these are the systems that operate similarly to air source heat pumps in that they use a refrigeration cycle to move heat around, but they use the ground as a source or sink of heat. And because of that, they can achieve very high efficiencies because they reduce the influence of weather on the heat source or sink. In 2023, there were geothermal heat pumps in about 1.3 million, or 1% of American homes, compared to 13% with an air source heat pump and 86% with no heat pump. And let's go to the next slide here. We can talk a bit about thermal energy networks, or TENS, where a series of GHPs connected together comprise a TEN. So it looks like, there we go. So let's drill in here for a second. They connect buildings via pipe fluid at ambient temperatures. They leverage all the benefits of GHPs, and they use shared boreholes and heat exchangers that are connected to a shared network of pipe fluids. So then they can boost or lower the working fluid to the operational temperature at the building level for heating and cooling. What I think is very cool about TENS is that different heating and cooling needs within the network can be met at the same time. So you can have a smoothed system. You can imagine a hospital that requires cooling even in winter for medical storage, say, that's connected to schools and apartments that require heating. So there's a give and take that leads to even higher efficiency. And as Jigger mentioned up front, infrastructure and capital needs to construct TENS can be bundled, so utilities can increasingly participate in their construction. So let's talk a bit about the geothermal heating and cooling value chain on the next slide here. It involves a number of different stakeholders and decision makers at every level, from the upstream and the light gray to the midstream and the medium gray to the downstream and the dark gray here on this slide. Each stakeholder has distinct roles, distinct responsibilities. They can be organized into international, national, regional, or even at the local level. And what's more, the way that they collaborate depends really on whether the construction is for a single building versus for a thermal energy network, or for a new build versus a retrofit. So I'm not going to go into full detail on this figure here. It's featured in the Liftoff report, but it maps the sort of complex interactions along the value chain depending on the installation type. Finally, I just want to go a bit into the value proposition on the next slide here. Stress that, as David mentioned, geothermal heating and cooling systems have a multi-pronged and a unique value proposition among building decarbonization technologies. So first, when you're accounting for weather across the US, GHPs have the highest coefficient of performance, which is a measure of efficiency, of all heat pumps in most states. So this high efficiency means that the potential for reduction in utility energy bills is also the highest among all options for heating and cooling. They also have large potential grid benefits and savings. So upgrading to GHPs reduces the peak load on the grid in all climate zones, in all seasons, except for winter peak load in cold climate zones. And in scenarios where there's high electrification, the grid benefits can also lead to large benefits in other parameters like summer and winter peak demand and cumulative system cost. So because of this, GHPs may be the best choice for heating and cooling in a number of geographies, and in particular in colder regions that also experience significant summer heat, like my home state of Massachusetts. They also have very long lifespans. Outside components can last 100 years or more. The heat pumps themselves are shielded from weather, also comparatively long-lived. And expenditures flow mainly to upstream and midstream stakeholders in the value chain, which are predominantly local and regional workers and small businesses, which creates local and regional jobs. Then there are additional benefits and advantages to TENS, which is a subset on the bottom here. In addition to the benefits described above, project level financing, as has been mentioned a couple of times, and rate basing for these systems means they can serve many customers who might not be able to pursue a single building solution. Gas utilities with decarbonization goals can consider TENS as a potential low carbon option for new infrastructure. And TENS, when deployed, also have significant environmental justice and equity benefits, with implications for many of the DOE's energy justice priorities. So for more information on all of these components of the value proposition, I refer you to the text of the report. And with that, let me pass it back over to Tim to cover Chapter 2.
Thank you so much. And sorry for a little bit of jumping around the slides there. I'm also running the slides here. I'm going to be taking you through our Chapter 2, which is basically our summarization of the current state of the market, focused on the technology markets. It's very numbers heavy. It's really focused on what is occurring now and what we know about the geothermal heating and cooling markets as it is now. So I'm going to start with these overall takeaways and go through some of these selected pieces of information. But this is a very number dense, very information dense chapter, and I definitely recommend you take a look at it because we've done some excellent work, I think, pulling these together. So overall, talking about the annual estimated installations of GHPs is that if we look at the year 2023, we think there's about a net addition of 85,000 units per year. That's meaningful, but it's not necessarily where we want to be, and it's not a lot compared to other heating and cooling solutions. We also really kind of looked at the cost of a GHP installation, which is highly dependent on the federal tax incentives, and is still generally the highest first cost option for anyone considering either a new HVAC system or a retrofit. We focused a little bit on examining the regional differences in GHP installation costs, which are really driven by the labor costs, especially the drilling costs, which can vary a lot based on the availability of the workforce and availability of the equipment, and well as some variability of the geology in the area. The cost of thermal energy networks can also vary wildly, and we're looking kind of at these different, generations of thermal energy networks where we have these projects that have occurred on military or school or campuses or medical campuses that have been in service for a while, that were built over the course of a long period of time. Also looking at these new pilots that are coming out that the gas utilities are putting together that have been so exciting. So we've been examining all of those things, and we have kind of a summary of the data as we have it now. But it's like I said, this is a living document, so there's definitely room for more people to give their input. So to start off, current GHP capacity stands at about 2 million units in service right now. So this is overall the units that are in service as we see them now, based on our best estimates of all these statistics of from the IRS, from the heat pump manufacturers, lots of data, a fair amount of uncertainty, but we're pretty sure we're on the right order of magnitude. You can also see that we have the estimated retirements down there, and as you can see, these stay in service for quite a long time. Just as we were talking about earlier. So we're building this thing, and I think a good number maybe to bring up here is when you're looking at this 2.1 million in service, is that annually about 3 million air source heat pumps and 3 million gas furnaces are installed each year. So we're really, as we saw in that earlier figure, we're a very, very small sliver of the market right now with geothermal heating and cooling. We should have got rid of that draft thing. This is no longer a draft, thankfully. So this is the estimated national median cost of GHP installation for a geothermal heat pump, both in a residential and a commercial installation. And you can see we really have, we've kept things, and this is very median, and you may have wildly different costs, and I've seen things differently both in both directions here. But you have a rather large capital expenditure that's split pretty evenly between the loop installation and the non-mechanical HVAC, and then a certain amount for the weatherization and retrofit cost that you may have to add in there. So if you're a new build, you don't have any of that cost, but if you're a older building, you may have way, way more than this that you're looking at. Then you have the tax credits that come in that in general offset, around 30% of the cost, that bring you down to a total cost that's a little bit more affordable, but still quite high on a cost per ton basis. And as you can see, that you have a lower cost on the commercial side of things, both because you have a little bit lower cost of the mechanical HVAC, and then also you get less costs on the loop supplies because you can build a larger system, which gets you some economy of scale going. I wanted to highlight real quick here, this is something that we did in a few different places. We looked at some economics of scenarios where you might have really, really affordable housing retrofits. So as you may know, there's a low-income housing tax credit that can, essentially be, it's either 9%, if it's awarded competitively, those are very specific areas, or 4%, which is the more common version of this. But those credits are awarded annually for 10 years, so you end up with 40 or 90% of the cost of your housing can be taken back in a tax credit. And so you can end up with these systems that cost quite a bit, but you're getting quite a bit of money back in your tax credit by building it out with this thing. So we wanted to really have this, highlighted here as these potential monetized credits and what you could bring in. And in cases where you can bring down the total cost of the system to be technically negative, or in many cases on par with the next most efficient option. A lot of this has to do with the ways in which geothermal tax credits are calculated, which has go into a lot of detail of that in the report. Moving on a little bit to another set of statistics that we pulled together was talking about the workforce that supports geothermal heating and cooling. You have, as you may have heard me talk, I was talking about a lot of different aspects in the installation, and you end up with a whole skilled workforce that supports these things. So we broke it out broadly into 4 categories of drillers, the pipe layers and the loopers. So people who are actually installing that ground loop, maybe after there's been some drilling occurred. You have the actual HVAC installers who install the geothermal heat pump in the facility or the house. And then you have the electricians who make, in many cases, very, very important upgrades that allow you to have an electrified heating and cooling system. So all of these things, you may have noticed, really serious training to get to the baseline level of being able to do these things. And, in many cases, you might be, if you're a driller, maybe you're specialized in a different type of drilling. So we focused and looked at the required training to get to a baseline level, and then what it might be to retrain somebody who is in a similar field to these things. So, as you can see, drillers be highly generalizable, as are electricians, because they have to do all sorts of things. And then the pipe layers and loopers and the GHP installers, there seems to be a lot of ability to retrain people from one side to the other, which is very helpful. But they're also in quite a big demand. So this is just a summary of this thing, and I'm going to use it to segue into our discussion here about kind of the workforce supporting this, which is, again, this is a relatively small workforce, especially the drillers. We have both drillers from oil and gas, and outside of oil and gas, and both of those together, barely, tops 30,000 right now. Which is just not a huge workforce, and it's highly regionalized. So people might have a small business that owns a few drill rigs in one part of the country, and having to scale that workforce up very, very quickly could be quite difficult. So this is one place that we've kind of identified as a possible bottleneck that could be addressed with some intervention on the public and private sectors. So with that, I'm going to pass it back over to my colleagues to talk about Chapter 3.
Excellent. Thank you, Tim. So chapter 3 covers the pathway to commercial liftoff and scale for geothermal heat pumps. I'm actually not going to go through the takeaways here for the sake of time because many of these have been brought up already. Let's jump right into the analyses that we want to highlight. So first, in this figure, we present 3 types of potential by year. So the economic potential is the top line, the market potential is the middle line, and the expected installation is the bottom line. Economic potential in this case is defined as installations with a positive net present value over 30 years. Market potential is installations with a positive net present value over 10 years. And the expected installation, it represents our understanding of current customer behavior, which is defined using an empirical installation curve that assumes a certain percentage of installations at different payback periods. So more details on these analyses in the report. Don't want to belabor them, but they are important concepts for how we got to our understanding of reaching commercial liftoff and scale. So in this figure, you can see that tens of millions of homes and businesses could install ground source heat pumps by 2050 with a positive lifetime payback. And these installations recoup the upfront cost through reductions primarily in the primary energy bill. However, not all installations with a positive net present value are going to be pursued for a variety of reasons, including upfront costs that are too high, cost recovery that takes too long, the disruption that could be caused by exterior or interior work, unacceptable installation time. Also, heating and cooling systems are frequently replaced with immediate need when a previous system fails. It may also just be difficult for customers to find the right service providers. So David's going to speak a lot more to the barriers and potential solutions in chapter 4. But I think the part of the story here is how the expected installation grows to the market and economic potential. So on the next slide, we can see that this is zooming in on just the expected and market potential, the bottom 2 lines. If the industry can maintain a roughly 10% growth rate from now to 2050, it could expand installations from that expected installation curve to its full market potential. In the US, the current industry growth rate is 5% a year. But the recent growth rate in the EU is closer to 10%. So this implies this is a feasible goal. And this growth, importantly, is achievable through 2035 by doing 2 things at once. So one is maintaining that expected growth in retrofit installations, and focusing on increasing the growth of installed systems in new build construction buildings, which have lower barriers for installations and will help make initial progress on sort of imperatives to scale for this industry. After 2035, that growth rate is achievable by maintaining the continued growth of installed systems in new builds and then growing the installed systems in retrofits. So in the next slide here, we can see our sort of pathway to liftoff and scale that we sketched out for this industry. The industry can reach liftoff by 2035 by focusing on these near-term opportunities. That is new construction for installation of ground source heat pumps in the equivalent of 7 million average size homes. Single building ground source heat pump builders can focus first on sort of profitable new construction and planned replacements with a necessary lead time to execute those profitable retrofits and scale the new builds to their market potential without unrealistic growth. TENS, thermal energy network builders, can focus first on completing pilot projects and then on expanding those pilots. And it's important that the costs for thermal energy networks continue to fall during this period, ultimately reach a sort of per unit parity with the cost for individual systems. And then the industry can reach commercial scale by 2050 by expanding and industrializing repeatable processes that include retrofits and build systems in the equivalent of 36 million homes. So let's take a look at a couple of the benefits here on the next slide. There are many that we explore in the report. I just want to highlight quickly the potential reduction in summer and winter peak demand. So in high electrification scenarios, without the expansion of geothermal heating and cooling, both summer and winter peak demand could grow significantly. but geothermal heating and cooling could reduce summer peak demand by 12 gigawatts and winter by over 40 gigawatts. There are other benefits from geothermal heating and cooling at liftoff. These taken together could reduce the overall grid system costs with a potential savings of $4 billion or 2% through reductions in capacity, transmission, and other maintenance needs, which we can discuss on the next slide. Here, this is just the savings, and then I just want to go to take a look at how these savings could be used to incentivize deployment. So on the next slide, we'll see that there's a potential pool of capital from these savings to fund incentives for ground source heat pump deployment. Though, of course, the exact mechanism, the level of the subsidy would be a legal, economic, and policy decision. But this experiment here demonstrates that about $2 billion in annual incentives to residential installations by 2035, which is half the expected grid savings from achieving liftoff in that year, could incentivize an additional 2.2 million homes equivalent to install ground source heat pump, geothermal heat pump systems, according to this analysis. So the recovery and reuse of the savings generated to the grid are on a similar order of magnitude as the total amount of incentives necessary to achieve liftoff, which is an exciting result that I think we wanted to highlight. So with that, let me hand it over to David to take us home with chapter 4.
Yeah, thanks, Charles. In chapter 4, just in the last few minutes here, we cover the challenges to mass commercialization and scale for the geothermal heat pump and geothermal heating and cooling industry. And we talk about ways that we can overcome those challenges at various levels of community and nation. We'll highlight just a few of them here, and you can read the report at your own leisure for some details. The first challenge, as we mentioned ad nauseum before, is that the GHP workforce really needs to be enabled and scaled up in order to build that groundwork for mass commercialization and have that ready workforce. And we'll talk about that in just in the next slide. That's patchwork of state and local regulatory frameworks surrounding particular drilling permits and worker and business licensing, utility system planning, and things like this. It's really important to have some sort of working together and having those become a little bit more compatible with each other, so that we don't work against ourselves. Having compatible local, state, national, and international technical standards also helps to enable this, and those technical standards can be advised by best practices that arise from early demonstration or pilot projects, and that's really important to driving economies of scale. We've also made a little challenge section that describes rate schedule innovations and incentives programs that can help make sure that utility customers who adopt geothermal systems or other energy efficient technologies are compensated or rewarded with those savings, and that helps align consumer behavior with management of future load growth demand. And as Charles showed very well in the last couple of slides, a lot of these incentives already exist, and in terms of the money that's available, they kind of pay for themselves in terms of reduced costs for grid build out. All we need to do is figure out how to make that link between grid savings and consumer benefits. And some of these programs are being trialed out by some utilities, such as demand response, and they're being implemented in a fair number of utilities as pilots and as new programs. We also think that additional demonstration projects or pilot projects can create these learning opportunities, best practices. We got to document them, we got to pass them down, make sure that the costs of particularly thermal energy networks and large commercial scale systems continue to fall. And taking together all of these factors can drive those network effects that support this prompt installation and then help reduce costs and timelines for GHP deployments. Next slide, please. We can, and to that first point about the workforce, we really need that rapid and sustainable growth of that workforce particularly in the drilling sector, but also in the other trades that are important for enabling that widespread GHP adoption. We go through this in detail in text, but one of the things that we can do is include more GHP installation training within HVAC installer training programs. Oftentimes, these training programs for because of the relative size of the air source heat pump and refrigeration market relative to the geothermal heat pump industry, the 1 to 16 difference. A lot of these training opportunities are not often included in standard HVAC training programs. And so oftentimes, like, even if a customer is interested in the geothermal heat pump system, a company that is installing typically other HVAC systems may not be able to offer geothermal heat pumps as an option to that customer, even if they're interested in it. Next slide, please. One of the things that we are doing about this as at the DOE here is we've launched, as Lauren mentioned earlier, a prize called the Geothermal Heat Pumps Partnerships to Accelerate Training and Hiring, or GHP Paths Prize. And you can find some more information about that in the link here on the slide, or by following that QR code there. Phase 1 submissions are open until February 12th. And this prize is really meant to stand up these regional train to hire partnerships and create those or enhance those existing GHP workforce pipelines in particular regions to accelerate that connection between people who want those jobs and want those skills and employers who have those good jobs and demand those skills. One of the other findings that we'll like to highlight, and we'll just wrap up after this, is that we find that capital costs to replace end-of-life natural gas distribution infrastructure are quite significant. And in Chapter 4, we have this figure, which goes into more detail there. In some cases, that capital cost to replace that distribution infrastructure for gas is comparable to or even greater than installing a standalone set of standalone GHP systems in all the residences throughout an area. And so here on the slide, we can see the capital cost for gas distribution infrastructure that could be avoided in gray, and then in dark green, the costs for installing an equivalent amount of geothermal heating and cooling capacity in those homes. And so the value proposition for electrified heating and cooling systems is the strongest when they're timed with the retirement of gas distribution infrastructure. And so allowing for those electrification upgrades to be paid by ratepayers within the rate base could help to alleviate that financing gap for GHPs and TENS. We could also minimize that potential amount of stranded gas assets that don't get renewed by deploying heat pumps where gas distribution systems are in need of replacement. And so that can help avoid shifting more of that cost burden of maintenance capital onto an increasingly smaller fraction of remaining gas customers. And so that the rest of this chapter 4, covers a number of the other sort of regulatory, business, and technology levers, like vendor engineering of heat exchangers and things like this, and to help achieve GHP liftoff by 2035. And we really encourage you to read that report for further details. Next slide, please. And we'd really, again, like to thank all the authors and contributors of this report, and as well as the extensive engagement and support from the private sector in terms of being able to find the facts that and put together those key messages in this report. As a final reminder, these reports are living documents. External engagement is what gives this meaning. You'll find a link to contact us about any feedback you have or any of the conclusions here at liftoff.energy.gov/input. Your input is valuable to us. You can also email us. There's an email address listed in the report as well. So with that, we'd just like to thank you very much. And that concludes this webinar on the pathway to commercial liftoff and scale for geothermal heating and cooling. Thank you.